Hello, fam. We're here for lesson 75. We're going to be talking about paired data today. And for me personally, I think that today's lesson, today's procedure is the most interesting kind of test that we can do for significance tests. So hopefully lots of you guys feel the same way. And even though it does take some work, at least it's interesting work. So we took a little break to talk about confidence intervals and how they're related to significance tests, and now we're back to doing a significance test. So we started with what are significance tests based off of? How do we state our hypotheses? How do we determine if there's convincing evidence? How do we decide if our p-value is low enough to be convincing evidence and reject the null? And then we talked about tests for p, test for mu, took a little break to talk about confidence intervals and significance tests, and now this is the last kind of test that we talk about in this unit, which is called paired data. So these are very similar to testing for mu. So very similar to the T procedure that we use to test for a mean. We're going to learn what a paired test is by looking at this first example. So researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, cola, and other substances with caffeine for the duration of the experiment. So this is the first time that we're talking about an experiment. We're not talking about a sample. We're talking about an actual experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake. So the idea is if we give them the same amount of caffeine, then they shouldn't be experiencing withdrawal symptoms. So for one 2-day period, they take the caffeine pills, and it's supposed to be the amount of caffeine that they're used to drinking. For the other 2-day period, they take a placebo pill, which is basically a fake pill. There's no caffeine in it. The two pills will look exactly the same. So our subjects will not be able to determine or know if they're in the 2 days of caffeine or if they're in the 2 days of placebo. They have no idea what they're taking. If they knew what they were taking, then that would cause a lot of issues with our results. The order in which they take the pills is what you randomize. So you don't want all subjects doing the caffeine pills first and then the 2-day placebo. You want it to be as random as possible. So you will randomly assign the order in which they take the pills. So half of your subjects will probably take the caffeine first and then the placebo, and then the other half of your subjects will take the placebo first and then the caffeine. So we're doing an experiment. We are looking at caffeine withdrawal, and to do this experiment, we are going to use 11 subjects. We're going to give them each a 2-day period with caffeine, each a 2-day period without caffeine. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. The table below contains the data on the subject's scores on the depression test. Higher scores show more symptoms of depression. For each subject, calculate the difference in test scores following each of the 2 treatments. So, higher scores show more symptoms of depression. The other thing that we are looking at is that we are determining whether being deprived of caffeine would lead to an increase in depression. So essentially what we think is that after the 2 days that they take the placebo, their depression rating or their depression score is probably going to be higher. So these two things lead me to believe that what we're looking at is whether or not the score is higher after the 2 days that they took the placebo pill. So what we are actually looking at is the difference in the depression scores between the 2 days. So this first line is the depression score after the 2 days that they took the caffeine pills. This row is their depression score the 2 days after the placebo. And we can see before even calculating anything that the depression scores for the placebo pills are a lot higher than the depression scores for the days they actually got to have caffeine. And remember, they don't know which day is which. So we want to carry out a test to investigate the researcher's opinion. I'm just looking for my pen as usual. We know at this point that that's basically my whole life, looking for pens. I'm really in a situation, hang on. Okay, we're going to carry out a test to investigate the researcher's question. So the idea here is that if caffeine has no effect on the depression score, then we would expect the difference between the two numbers to be 0. If caffeine has no effect on their mood whatsoever, then we would expect these depression scores to be exactly the same. So whether they just took the placebo or the actual caffeine pills, subject 1 should have rated his depression at 5 for both days, both sets of days. This should both be 5, both 5, both 3, both 8. If there really is no difference, if caffeine really has no effect, when we subtract these numbers, we should be getting 0 because they're exactly the same. So what we're testing then, our null, is that the mean of our difference. So we're writing mu sub d. That d stands for difference. We're testing that that difference is 0. Remember, our null is always equal to. And for a paired test, it's always equal to 0. The alternative then, well, we have, stated here that we think being deprived will lead to an increase in depression. And if higher scores mean more, quote unquote, more depression, that means when we find the difference between the placebo and the caffeine, it should be positive. The difference should be positive. So we're expecting our difference to be positive. So why is that? I'm going to write here why that is, but it is not required. This is not part of the response. I'm writing in for you guys why we would put a greater than here. So we use greater than because we expect the placebo group to, not group, I shouldn't say group, the placebo days to have a higher depression score. Okay, then we define our variable, where this new mu sub d, is the true, let me verify real quick that that blank is really the word true. No, actual. Where mu sub d is the actual mean difference. And when you are defining this, when you decide what your mean difference is, you have to clearly write what order you're subtracting in. So up here, we're doing the placebo score, subtract the caffeine score. So up in our table, we're going to do this in the order of the placebo subtract the caffeine. So where mu sub d is the actual mean difference in depression score for subjects like these. No significance level is given, so we will use alpha is 0.5. So before we move on to our plan, we have to go up to the top and actually find our differences in depression score. So luckily these numbers are easy for me at least to do in my head. So I'm doing, notice, I'm doing placebo minus caffeine. And here I'm going to highlight again that we have to define that in our hypothesis statement. Okay, 16 minus 5 is 11. So the difference for subject 1 was 11. For subject 2, we do 23 minus 5. That's 18. 5 minus 4, 1. 7 minus 3, 4. 18 minus 18. 14 minus 8, 6. 24 minus 5, 19. 6 minus 0, 6. 3 minus 0, 3. 15 minus 2, 13. 12 minus 11, 1. 0 minus 1 is a negative 1. I'm just going to double check my numbers really quick. And then I'm going to highlight. As expected, most of the differences are positive. Why did we expect them to be positive? Because up here we have that higher scores show more symptoms of depression. And we think that the depression will be higher after the placebo days. So as expected, our sample values are mostly positive, which matches our alternative. That's why I have all these statements highlighted in the same color, because they're all related. What's our plan for this guy? Well, what we're doing is a one sample paired t-test for mu sub d, and that's written here at the top. So we've talked about a one sample z-test for p. We've talked about a one sample t-test for mu. And this guy is a one sample paired t-test for mu sub d. Make sure that you have there mu sub d. Okay, randomness in this case is different because we didn't randomly select these 11 subjects. We had to find 11 subjects that were caffeine dependent. We still have to have randomness, though, to make this valid. And in this case, where the randomness comes from is the order in which we assigned the pills. So researchers randomly selected the order of the treatments. And in this case, treatment 1 was caffeine, treatment 2 was placebo. You don't have to write that down if you don't want to. I'm just making it clear what they mean by treatment. 2. N is less than 30. It's much less than 30. So we had to graph this sample data and determine if we're allowed to use a T procedure. So the most important thing that I'm seeing in the box plot is that there are no outliers. Your textbook also says or describes this as some skew. Now to me, that's definitely right skewed. But your textbook would label this as some skew. Histogram does not do me any good. I don't know why your textbook provides this. And your textbook says this is not helpful. They graph it and then they tell you the histogram doesn't really give you helpful information because your sample size is so small. So I'm just going to completely disregard the histogram. This guy, though, is our NPP, and he clearly has a curved situation going on here. Well, what this means is that there is mild skew. The curved appearance means there's mild skew. I'm not sure what it would look like if there was like strong skew, but that curved appearance indicates that there's mild skew. Now, typically, when they have you graph to determine if you can run the test, 9 times out of 10, they're intending you to run the test. So as long as there's no outliers, I would usually move forward, even when it's obviously skewed, and this guy is not very linear. You definitely have curving there. So even though I'm thinking, I don't know about that, I'm going to move forward mostly because there's no outliers. And I feel confident moving forward because I know from experience that 9 times out of 10, they want me to move forward. They want me to complete the test. I know for sure they want me to stop, though, if there are outliers. So be on the lookout for that. Then our last thing, so N is less than 30, but the box plot shows that it's reasonable to use T procedures. Now, I mentioned this in class for one of my classes. You have to label the graphs if you're going to make this statement. So if you're just saying the box plot shows that we can run the T procedure, on the box plot, you actually have to write how you know that. No outliers, some skew. If you don't write on your graph, then you have to write here, the box plot has no outliers and only shows some skew, so we can use a T procedure. I find it easier to just label the graph and then make this statement. Lastly, we don't need to check the 10% condition in this particular problem because we're not sampling. We're doing an experiment. We're not sampling. We're doing an experiment. It just occurred to me up here that I should probably really write C graphs, just to indicate to your AP grader, your AP reader, whoever grades for you, to look at your graphs and you explained there. Usually they will look at your graphs to see if you justified your reasoning or justified your response, but it is certainly helpful to tell them to look at your graphs. Okay, the do. Well, we need some information in order to do the T critical. We need our degrees of freedom. That's going to be 10. We need our X bar sub D. We need the mean of our differences. And we need the standard deviation of our sample. So this comes from your calculator, one variable stats. So you should enter in these 11 values into your calculator and run your one variable stats. Pause the video and really enter them and run your stats so that all you have to do is double check your values against mine. Pause. Okay, welcome back. Hopefully you really tried it. So I got a sample average of 7.36 and a standard deviation of 6.92. I could be wrong, so if yours is different than mine, double check the data you entered, and if you're sure I'm wrong, then don't freak out. Carry forward with the numbers that you know are right. Okay, to find my T, I take my sample value, 7.36, subtract my null value of 0. There's supposed to be no difference in depression score. Divided by my standard deviation of 692 over root of my sample, which is 11. Then you guys know that I prefer to calculate this by running the test in my calculator. And for this data, it's the same test we've been running this entire unit. So we go into stat, we arrow over to tests, we choose option 2. I'm going to enter in data because I entered in the actual data. Your mu sub 0 is 0. Your null mu is 0. I believe my list is 2. We'll see. And I am doing a greater than. We think that the difference is actually greater than. I'll do a calculate. So I get a T value of 5304. So 3.5304. And I'm going to 4 decimal places because that's what I have to look up on my, oh, that's only 3 decimal places. Just kidding. So I'm going to go to 530 because inside my table, they go to 3 decimal places. Okay, then I have asked you guys to practice both finding it from the table and from your calculator. Well, we already have the calculator one. Your p-value is 0.0027. From the table, I'm looking for 3 point, and then I'm going to think about that as 530. So I'm going to go to my degrees of freedom 10. It's at the bottom of a gray panel. I'm going to go to the 3s probably. And I'm looking for it to be 530. Is that true? Yeah, 5304. I'm going to enter in our... Hang on, I'm just double checking my numbers. I'm going to see what you get if you enter in the stats instead. So we got 7.36, 6.92. So if you entered in the stats instead, you would get a t-value of 528. So if you got 528, that's okay. You're going to end up with the same p-value that we did. Notice here that that p-value is still 0.0027. So you're either looking for 528 or 530. Because we used stats, because we used data, the actual data, ours is 530. If you use stats, like in this problem, I've already done this problem. I had to practice it first. I did stats and got 528. Okay, so back to the 10 degrees of freedom. 530 is between 169 and 581. So my p-value, according to the table, is between 0.0025 and 0.0050. I'm doing them both to 4 decimal places. However, I know that it's going to be way closer to this value because mine is 3.530. This one is 3.581. So I know it's going to be closer to this than this. And that's what we end up getting from our calculator. So what is our conclusion? 20 minutes later, what is our conclusion? Since the p-value 0.0027 is less than alpha equals 0.5, we reject HO. We have convincing evidence that the actual mean difference in depression score is positive for subjects like these. So remember, when you make your conclusion, you conclude based off of the alternative, whether or not you reject the null. So we either have convincing evidence that it's greater than 0, or we do not have convincing evidence that it's greater than 0. So here we have convincing evidence that caffeine leads to caffeine withdrawal. People being deprived of caffeine leads to an increase in depression. So how did we figure that out? We tested whether or not the difference is 0. If the difference is 0, there's no caffeine withdrawal has no effect on your mood. If it's greater than 0, then we have evidence that caffeine withdrawal does have an effect on your mood. So what this means down here, just to make sure that we're all on the same page, is that the placebo days experienced higher depression or more depression, or however you want to say that. And you don't even have to write that. I'm just making sure that it's clear that what we just concluded was that after the placebo days, the depression score was higher. Okay, one more problem before you try this on your own, but luckily this problem is much shorter, partly because we don't have to graph, partly because now you know the process. So all soda pop becomes less sweet over time. I did not know that. I did not know that until I started teaching AP Stats and did this problem. So all soda becomes less sweet over time. And diet drinks expire the quickest. The population distribution of sweetness loss is approximately normal. Here are the sweetness losses from a random sample of 10 batches of Diet Coke. Is sweetness stronger before? Is sweetness stronger before? So that means what we're testing is the before subtract the after. So before is B, after is A. To find your difference, you are going to do 3 minus 1. That's going to give you 2. 2.8 minus 2.4, that gives you 0.4. 3 minus 2.3 gives you 0.7. And I'm going to let you finish the table for practice. Once you finish the table, enter the data into your calculator just like we did on the previous problem. So you're going to need to pause to do that. When you have all the differences and you've entered them, come back. Welcome back. Hopefully that's really a welcome back. You guys probably get so tired of hearing me say, hopefully you really did it. So I'll try not to say that anymore. Okay, we want to perform a significance test at, well, they didn't give us a value, so I'm just going to write the default alpha. Using the hypotheses that the mean difference is 0, because if time has no effect on sweetness, then we would expect the actual mean difference to be 0. If time has no effect, then that means the sweetness level for both of these should be 3. 2.8, 3. We are testing it against the alternative that it's stronger before. So that means if we do before, subtract after, we should have positive numbers. This is where mu sub d is the actual mean difference in sweetness for Diet Vanilla Coke before and after storage. But remember, you have to explicitly define that you are calculating the difference as the before sweetness subtract the after sweetness. What's our plan? Same as last time. We're doing a one sample paired t-test for mu sub d. This time we're not doing an experiment. We're not assigning a treatment to anything. So we do have to have a random sample. And a random sample of 10 batches was taken. We do have to check the 10% condition because we are sampling. Last time we didn't have to check it because we were doing an experiment. This time we do. So N is all batches of diet vanilla Coke. And what we usually write here is, so it's reasonable to assume that 10 is less than or equal to 1/10 capital N. This is an example of another way that you could check the 10% condition. So if you prefer to write, so it's reasonable that, go ahead. This is just one alternative, one different way to check the 10%. So if there are at least 10 times our sample size, which is 10 times 10, which is 100 batches. So N is all batches of Diet Coke. So if there are at least 100 batches in the population, then N is less than or equal to 1/10 N. Now, if that does not make sense to you at all, then you just write N is all batches of Diet Vanilla Coke. So it's reasonable to assume that 10 is less than or equal to 1/10 N. You don't have to do it this way. Third condition, N of 10 is less than 30, but hallelujah, the population's distribution is stated to be approximately normal. So we can use T procedures. We can use T procedures. The do, we need to have our degrees of freedom. We need to have our sample difference. We need to have our sample standard deviation. I am not going to fill those values in because it is imperative that you guys know how to get those from your one variable stats. So do that and then come back to find T with me. T is the sample difference you found, subtract the null value of 0, divided by your standard deviation over root 11. Just kidding. Root 10. We looked at 10 batches of Diet Coke. If your mean and your standard deviation are correct, you should be getting a T value of 2.697. If it's slightly higher or slightly lower, you're fine. Like in the last problem, if you used stats, you got 528. And if you used the actual data, you got 530. So if it's pretty close, you're fine. But if it's more than a couple of decimals off, like if it's not like 695 to 67 or 0.7, then you might want to check. Okay, from table, your range, your p-value range is from calc, your p-value is find them both. Pause and find them both. So from the table, it's 1% to 2%. It's closer to 1. I am not going to list the value for you because I think that it's important that you calculate some of this stuff on your own. Whatever you get should be close to 1%, or you can think about it as 0.0100. So your p-value is close to 0.0100. Since the p-value, and I'm not going to give it here, is less than alpha of 5%, we reject the null. We have convincing evidence that, and now we want to frame it in terms of the alternative hypothesis, that the actual mean difference of sweetness for Diet Vanilla Coke is greater than 0, which means Diet Vanilla Coke is sweeter before being stored. So that means if the Coke's been sitting on the shelf for a really long time, it's probably less sweet. And if you prefer your Coke to be really sweet, then you want to make sure you check expiration dates. So a little bit of a true story. Everybody that knows me, that really knows me, and like some of my, well, not some, a lot of my students know this, that my favorite candy is Reese's. But I will only eat fresh Reese's. And I've said this to people before, and they're like, what do you mean a fresh Reese's? Like, Reese's or Reese's? And I'm like, guys, you don't know what you're missing until you have a fresh Reese's. So whenever I buy Reese's, I have to go in and check all the expiration dates. And if the expiration date isn't like 7 months away, I won't buy them because they won't be good. So now you know the secret. It's kind of, this problem made me think of it because maybe there's such a thing as like a fresh soda. So if you like sweet soda, you want to get it when the expiration date is really far away. I should do a test on whether or not Reese's are better before they're stored. And the answer is yes, they absolutely are better. So what we did today are paired tests where we compare two different values to each other to see if there's a difference between two things. So in this case, we found out that people who are going through caffeine withdrawal usually have a higher depression score, so they are probably feeling a little moodier than somebody who's not going through caffeine withdrawal. And then on this page, we learned that Diet Vanilla Coke is sweeter the farther away from its expiration it is. So Diet Vanilla Coke is sweeter before you store it. As time passes, it's proven, it's shown, it's been tested that it loses sweetness. So what you have left to do for this lesson then is this floral problem. You have to do it from start to finish. Since they're giving you the data, you are going to have to decide what you're subtracting. You're going to have to make a graph to verify you can use T procedures, and then you have to find your conclusion. So as with every check your understanding, this is a check your understanding. I'm not sure why I didn't put check for understanding there. So I'm going to write that in now. This is your CFU. Really give it a go before you watch the solutions, okay? Hopefully some of you guys found this enjoyable, because I really enjoy these. All right, love you guys. Hope you have a great day or weekend or, I don't know, middle of the night whenever you're doing this. Okay, love you.